this interval here kind of shrunk, right? What would I have to do? All you gotta do is just increase your sample size. That's all you have to do. Costs more money though, doesn't it? Yeah, people aren't getting paid for free here at Gallup. They're gonna work, so. Leads us to this question. All right, so letter F. Everyone, in letter F, what we're gonna do is we're gonna talk about, we're gonna determine a sample size. Determine the sample size necessary bless you, to obtain a margin of error. I'm making this up, everyone, I'm going to pick a number smaller than this, 2%. A margin of error of 0.02. And this is with the same level of confidence, which in this problem was what? 95% confidence. All right. Now, this formula is not on the formula sheet. Let me write it here. Sample size equals P hat times Q hat all over Mo over Z squared. And this formula, though, is not on the formula sheet. So I'm just going to type all this out. You know, when I'm going to get a number, do you all agree this number is going to be more than the 1,050? Yeah, it's going to be bigger. Well, let's see what we get. All right, what goes there? I'll go up to 4 places. 0.4695. Good. Times. Times, not plus or anything. It's a multiplication. Everyone see that? Times. What was Q hat?
0.5305.
All right. And then I'm going to hit division. I'm going to hit a parentheses. This time, be careful when I'm not talking about that margin of error. We want the smaller margin of error of 0.02. There's going to be a squared here. Now this number, this is going to be a z value. I don't see it anywhere on the board. So we got to talk about that. How do I get this z right now and I'll replace it? Let me just put the yellow chalk number here because we're like, uh-oh, I don't know how to get this. And you're going to help me with this.
Inverse norm.
You got your t-tables? I recommend right now you pull out your t-table.
What will be the inverse norm?
Yeah, absolutely. So I'm going to use Art's method afterward. I'm going to start with this. You said, hold up, that's a t-distribution. Yeah, but what's at the bottom part of this table right here? Yeah. Because eventually when the sample size reached, millions, approached infinity, you get down to these row of z's. So go match up 95% with the z-score. What do you get?
1.960.
You got it. Now I'm going to talk about what Art just mentioned. You go, well, is there another way to get that number? And Art, could you tell everyone another way to get this number right here?
Okay, you do inverse norm.
Inverse norm button off your calculator if you wanted.
And you have to do like 100 minus 95.
I'm going to draw a picture so people see it. He's saying if you get 95% in the middle,
Yep.
you got to type into the calculator what's over there in that left tail.
0.025.
Yep. So when I'm going to put that, it'd be 0.025. This would also work on your calculator. It'll come out negative, but that's okay because we're going to square it.
Why is there a 0.02 instead of a 0.03?
Right there, great question. In this particular problem, we know we found that for the Euler part. Let me just put a line here. I'm like, okay, we got 3% there. We said, what would you have to do if you wanted to decrease the margin? Well, you have to increase your sample size. So these two are kind of going together. We're saying the question goes, what would you have to do to obtain a margin of error of 0.02? So that's why we're using that. I do want to point something out though. If you accidentally did that on a test, you're going to come right back to that number. And you would probably catch it. You'd go, wait a minute. Oh, I got you. I gotta use that number. You just put yourself right back at that 1,050. This is going to be a bigger number. So is everyone okay with that? These are two ways to get this z-score. Do you prefer the table or the inverse norm button?
Can you tell me one more time how to find it on the table? I mean,
Absolutely. Because we get here and you go, all right, well this is a t-table. Remember the thing about the t-distribution? As the sample size just got bigger and bigger and bigger and approached infinity, which was based off the degrees of freedom, the t-distribution turned into our normal distribution, the z-distribution. So we look down at the bottom, we look at the row for z values, but we gotta line it up with all those percentages right below it. See those percentages, those are confidence intervals. And right below we look for the percentage that's 95% in the very, very bottom row. Do you see it? And right above it is the 1.96.
Okay.
But if you want to look at the top, that's okay, but you gotta be careful. If you look at the top row, this is the number you're gonna look at. Because you gotta look at what was in one tail, if that helps. So that's why I always draw pictures. Because Art does this, other students like technology. We gotta be careful how to get that 1.96. All right, let's see how big this is. How big is the daggone thing? And I'm just gonna go to a blank screen.
You said that formula is not gonna be on the.
That's right. So it's the only one we'll just know. P hat times Q hat divided by mo over z squared in parentheses. Hey, before you leave today, see me about that too. All right, 0.4695 times 0.5305, right?
Yes.
Division. But I need a parentheses now, right, Ellen? 0.02 division 1.960 raised to the second. We always round this number up no matter what. We always round up so it's within. So can you just round it up to the next person? 2,300 and how many people?
93.
2,390. Don't go down to 2. Always round it up to the next integer. There you go. 2,393 people is the answer to the letter F. That's your sample size. Now, I'm looking. Did anybody not get that number? Well, I gotta look at your calculators. No, all right. Aspen, did it work?
Yeah.
Oh, sweet. Everyone's good?
So like, if we don't remember to round the number up, you're gonna mark it like totally wrong.
50 points off.
Oh, God.
How did you get the 0.025 again?
All right. That would be if you didn't use the table.
Yeah, if you weren't using it.
So what we did was, because it's 95% from the middle of this bell curve,
Oh.
so we took 100%,
Oh, okay.
subtracted 95%, divided it by 2. Cool. Some of you are like, I didn't do that, I just used the table. The two most popular z-scores, you've probably noticed. One of them's 1.96, the other one's 1.645. 1.96, isn't that close to what number? What integer? 1.96 is about a what?
2.
2. 2 standard deviations, remember that? The empirical rule? If you're 2 standard deviations away from the mean, right? 95%, yeah? Okay. All right. I got a question for y'all. Ready? We're about to talk about using t-scores and all that stuff with means. Can I erase? Yeah? All right. What is the important criteria for why we use t rather than z?
Well, the
When
sample,
doing inferences
sample size is small.
about populations. Did you want me to write it down? They're like, yeah, you're just talking up there. All right, here it comes. I'll get this out of the way. Everyone, what is the key, like the important criteria? We're using t.
You're gonna ask that on the test? That's what all I need to know. I think you're gonna ask that. You gonna ask that?
Rather than
I'm just saying. This not me, let's say it.
the z distribution.
I don't know. No, that's general Ross. No, I thought that he was the one. I don't remember.
When performing inferential statistics. All right.
Okay,
So everyone, let me just repeat this so it's clear and people go. What is the key criterion for using the t-distribution rather than the z-distribution when performing inferential statistics? By this phrase, inferential statistics, I'm talking about we're doing confidence intervals and we're doing population, hypothesis tests. And we'll come up with the solution to you.
First of all, I didn't know, what is the circle, whatever?
Sigma.
I know this
Oh,
one,
sorry.
so sigma.
Standard deviation.
Right.
Yeah, that's
so
sigma.
Sigma population standard,
Yeah.
that population standard deviation is unknown. That's
Okay.
what you stated.
So this right here is the Greek letter sigma.
Sigma.
It's lowercase sigma.
Okay.
It represents a population, not a population mean, but a population standard deviation. And something had to do with this, which is the key criterion. This thing was just unknown. This was what caused the whole thing. So there's the answer. The population standard deviation is unknown, which really created this whole thing going back to that fellow named Gossett, who worked for the Guinness Brewery, right? That was the key criterion. It made us go, all right, we're going to use T rather than Z when we're doing inferential stats about population what? When we're doing inferential statistics about population means. Okay? So that's the answer.
Oh, okay.
So everyone, we all know when we're doing all this stuff and we deal with means, we're not going to use the z-distribution, we're going to use the what? The t-distribution, true? We didn't use it on my first problem. Yeah, because that was a proportion. Cool.
And that, I mean, I get that right. I can get that question right. And,
Can I erase?
you said that T distribution becomes the Z distribution when n equals, what that mean?
Infinity, yeah.
Right. Oh, T.
Want me to repeat it?
Yeah.
All right. You got this?
Yeah.
This is a t-distribution. Right?
Uh-huh.
In this left column, you have what's called degrees of freedom.
Right,
And the numbers get bigger and bigger and bigger. They're based off the sample size.
gotcha.
As the sample size, degrees of freedom also, as it approaches very, 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 very big numbers. So you and I think, what's the largest number in the world? As it approaches infinity, the t-distribution will actually become done, we're way, way at the end, what letter?
The Z.
Z-distribution.
Okay.
Just
See,
double check it.
Awesome. The t-distribution changes based on the sample size, doesn't it?
Yeah.
Thanks to Gossett. See, does that make sense? Awesome. All right,
The T becomes Z when n is infinity.
9.2.
Pass.
We're going to do a confidence interval about a population mean. So I'm going to pull a problem from 9.2. I thought I'd select number 29. Blood alcohol concentration. A random sample, and this has come from 9.2. I'm taking number 29 if you're curious. I'm going to take number 29, but here's what happened. They did a random sample, everyone hear that word, random sample? Of 51 fatal crashes in the year 2009. All right. This was the mean BAC. We're talking about the blood alcohol concentration. We all know, like, you can get in trouble if you're on the road, it's higher than 0.08. This was with the fatal crashes, all right? The mean BAC was 0.167. All right, this is in the year 2009. The standard deviation was 0.01. All right. And how many crashes was it?
51.
51. All right, Owen, do you see mean?
Mhm.
Right, this was a sample mean average. Those are the mean numbers. Standard deviation 0.01. 51 fatal accidents. But this is mean, so we are going to have to consider in this problem here, Sierra, degrees of freedom. So I might as well write it down. What's DF?
50.
Yeah.
N minus,
N minus 1, don't agree?
yeah.
So I might as well write it down, since I know I'm dealing with what? Means, right? We're going to use the t distribution. We'll use this, we got means, but I might as well write it down. Degrees of freedom, you got 50 degrees of freedom. All right. Anything else? Well, it's going to come up, they're going to say what confidence interval they want. So, hey, letter A, can you verify requirements? Now this time, everyone, this is not the MPQ greater than or equal to 10. In this problem, everyone, because we're dealing with means, if we want to ensure that the sample distribution of that sample mean, you know, if the distribution of the sample mean is approximately normal, the sample size has to be greater than or equal to 30, is it?
Right.
All right, we're good. Is it a random sample? Check. Let's roll. Whoops. Woo. We got a random sample. We're rolling. Don't agree? Can the sample size be smaller than 30? It can if they have knowledge about the population already being normally distributed. Okay? So don't get thrown off there, Mia, when you think, are they trying to trick me? Sometimes in a problem, you go, is the sample size greater than or equal to 30, or this stuff, you go, if it's not greater than 30, I stop. Well, if it's sample size like 20 or 15, maybe they said they have knowledge of the population already. Like with gestation period, where we already know that the distribution for the gestation period for the population is already approximately normal. Then we don't have to worry. Does that sound good?
Yeah.
But you'll see that on the check. I wrote that. I put that down that, you know, who cares if your sample size is really small if you already know that the population, all right, not sample, but the population is normally distributed. All right, letter B, everyone, you're going to construct, this time not 95%, a 90% confidence interval. All right. Where are we going? Hit it, everyone, hit it!